We will start today's class. In this lecture, we will discuss the design of subsurface drainage system. Three steps in that. Second, third, and fourth step. The second step is we are finding the depth and spacing of the drain. The third step, we are finding the capacity of the tile drainage system. And in the fourth step, we are finding the size and grade of the tile lines. So we will see each of them. Before that, we will just analyze what were the steps. There were 8 steps: layout, depth and spacing, capacity, size and grade, material, load, envelope materials, and installation. So these were the steps. Out of that, layout we have discussed. Now we are moving on to the second, third, and fourth step. First, we will see the second step. So after deciding the layout, we have to find the depth and spacing. So in that, there are two things. One is depth and the other one is spacing. First, we will see spacing. So we have already derived the equation for spacing. By using Hoogout's equation, we can derive the spacing. Okay. So this was the equation which we have derived. The derivation is already given to you. So you know that this was the figure for derivation. In this, actually, they have given an open drain. A surface, maybe it may be a surface deep drain, but still the same equation can be used for the subsurface drains also. Okay, for derivation purpose we have used this figure, but it can be the same equation can be used for subsurface also. So this is the equation for finding the spacing between two drains. Okay, so in a field, you have to assume a field first. In that field, there we need a large number of drains, okay, for draining the total amount of excess water. So we need a number of trains. The spacing between each trains should be equal. Okay. So in that case, how we can calculate the spacing? How much space should we provide between the trains? That is calculated by using this Hoogout's equation. Okay. So the spacing between two laterals or the spacing between two mains can be calculated by means of this equation. Okay. In this, D is the elevation of water level in the train. So all these things are given in this figure. So it is known to you. And in clay and clay loam soils, tile is generally spaced 12 to 21 meter apart. Okay, so that much distance will be provided for the tile drains when it is installed in clay or clay loam soils, because clay is a type of soil which has less transmissivity of water or less permeability of water. Okay, in clay soils water will be less permeable, so there not need not be large number of trains is not needed there. Okay, so trains can be placed at a large spacing there. So we need only 12 to 20 at 12 to 21 meter, there should be one train. Okay, in silt loam soil, the tile is spaced 18 to 30 meter apart. So 18 to 30 meter is for silt loam. It is also a similar kind of soil as that of clay. In sandy loam soils, tiles have to be spaced 30 to 90 meter apart. So in this case, what is the thing is, in clay soil, the water holding capacity is higher. Okay, so water needs to be, and the movement of water will be lesser. So we have to, I am sorry, I made a mistake there. In clay soil, the water holding capacity is higher, and the water will not be permeable. So we need the drains at some spacing, some closer spacing we need the drains. In case of sandy loam and all, what is the peculiarity of sandy loam soil? It is a coarser soil. Okay, so what is the peculiarity? It has larger sized pores. So the water can easily move through the sandy soil. So the speed of the water will be higher. So we need the water can easily move. Since the water can easily move through it, the tiles can be placed at 30 to 90 meter apart. So it will finally reach the tile drains after moving 30 to 90 meter. So this is the thing. The spacing of drains will be higher for sandy loams or coarser soils, and the spacing is lesser for clay type soils. Okay. That's the thing. A spacing closer than 50 meter usually makes the drainage too expensive. Okay, when we are giving a spacing of less than 15 meter, we need large number of drains, right? When the spacing is less, that means we need large number of drains. So it will be too expensive. Okay, so we have to consider this economic concept also. And regarding, so this is about spacing. Now another thing we have to consider here is the crack width of the tiles. So how the water enter into the tiles? Actually, you know that we are placing some pipes, short length pipes below the soil. Okay. So how the water can enter into the pipe? The pipe will not be perforated. Okay. Then how the water enters into the pipe? We are placing the pipes without joining them each other. Okay, there will be a number of small length pipes, and we are not joining them each other. So there will be a crack between each pipelines. Okay, in the lateral itself there will be a number of, there is one lateral. In that lateral itself there will be a number of short length pipes placed. Okay, without joining each other. So in between the two pipes there will be some space. Through that space water will enter into the pipelines. So that space is known as crack width. Okay. In the case of tile drains, water must enter the drain through the space between the successive tiles. Tiles is otherwise known as pipes. Okay. So pipes are known as tiles. Doubling the crack width increases the flow into the drains about 10% under ponded condition. If the soil above is well saturated, then if you are doubling the crack width, more amount of water will enter into the tile. But if you are increasing the crack width very much, then it will not be good. Okay, the water will not correctly reach the tile. It may go infiltrated or deep percolated. Okay, so the crack width should be in such a way that the water will be allowed to move into the pipelines. Okay. The maximum permissible crack width usually recommended for silt loam soil and silty clay loam soil varies from 1 millimeter to 3 millimeter. That will be the distance between two pipelines, 1 millimeter to 3 millimeter in silt loam and silty clay loam. For sandy loam it will be higher. Okay, that's the thing. And the second thing in this step is depth of the drains. So we are placing a number of pipelines below the soil and we are refilling the soil. So how much depth we have to place these tiles? So actually what we are aiming at is we have to remove the subsurface excess water. So we are removing the water below the root zone. We are placing the tiles below the root zone and we are trying to extract the excess water from the root zone. So there should be a particular depth up to which we can place the tiles. Okay, so that is the depth of drains. The depth and spacing are closely interrelated. Okay, depth is when spacing is higher, depth has an influence. Okay, we will see that later. Actually, depth is measured as the distance from the ground surface to the bottom of the tiles. Okay, and the depth depends on this much parameters. It depends on the texture of soil, hydraulic conductivity of the soil, the type of the crops grown. Because if the crops have much capacity to extract the water from the soil, then the depth should be lesser, higher. Okay, so the crop roots itself will take more amount of water. So then the tile drains can be placed much deeper. Extent of surface drainage, outlet condition, topography, salt content. So all these factors will depend on, influence the depth. Okay. And the depth of the tile drain should be such that the water table should be at a satisfactory depth at the midway between the drains. We have to minimize the water table or decrease the water table. So we have to place the tile drains in such a depth such that it can extract the excess amount of water from the root zone. Deeper the drain, wider the spacing, lesser the number of drains required. So actually first we have seen that the depth and spacing are interrelated. So this is the relation between the depth and spacing. When the drain is deeper, we are placing the drains at a deeper depth, then the spacing can be wider. Okay, we can place the drains in a larger spacing and lesser the number of drains required. Okay, so this is the thing. This you have to think logically and understand. Tiles are placed above impermeable layer if any. If there is any impermeable layer, we have to place the tiles above the drains, above the layer, because if there is an impermeable layer, then water will not fall below that. Water cannot transmit below that. So we will place the tiles above that impermeable drain. Deeper drains result in high installation costs. Drain depth from ground surface to the bottom of the tile is usually 1 to 1.5 meter. Usually we will place the drains at 1 to 1.5 meter below the ground surface. Because why we are choosing this 1 to 1.5 meter is, most of the crops have a root zone of up to 90 centimeter. 90 to 1 meter, okay, 90 centimeter to 1 meter. So that's why we are choosing a depth of 1 to 1.5 meter for placing the tile drains. And it depends on the soil also. The depth of the tile drains depends on the soil also. In sandy soil, the drains are placed deeper and farther apart, while in clay soil, we will place the what is that the drains at a close depth, that is 75 to 90 centimeter deep. We will place the drains. In silt loam it will be 1 to 1.2 meter, and in sandy loam it will be 1 to 1.4 meter. So that is about the type of soil. Now we will move on to the third step. So now we have discussed the depth and spacing of the drains. So after discussing the depth and spacing, the next thing we have to see is how much is the capacity of the tile drain. So we are going to install a tile drainage system. Now we have to discuss about the capacity, how much amount of water it can transmit. So that is a very important point. We have to design the tile drain before installing it. So we have to know how much amount of water it can capture from the area. So this comes under, this capacity and all comes under the hydraulic design of the tile drain. So design capacity of the tile drains is based essentially on the drainage coefficient. You all know what is drainage coefficient. It is the total amount of water that a drainage system can extract within 24 hours. Okay. Capacity of a drain depends upon its drainage coefficient. Normally when in rainfall areas, the drainage coefficient mostly depends upon the rainfall. Okay, when there is excess rainfall, excess amount of water will be stored in the soil, so the drainage will be higher. So drainage coefficient also will be higher. When annual rainfall varies from 750 to 1500 millimeter, the usually adopted value of drainage coefficient is 10 to 13 millimeter per day. So we will assume the drainage coefficient. This much amount of water should be taken out from the area in 24 hours. Then what will be the what should be the capacity of the drain? Like that we have to do. For organic soil or for high crops, the drainage coefficient value is increased by 30 to 50%, and when there is surface runoff to be carried by the drain, then the drainage coefficient should be doubled. 20 to 25 millimeter per day water should be taken out. Okay. And in irrigated areas, the expected value of the drainage coefficient is 10 to 50% of the water applied. And in irrigated areas, the drainage coefficient depends upon the depth of irrigation, the method of irrigation, leaching requirements, soil characteristics, etc. These all are non-thing. Okay. And the drainage coefficient is calculated as per USSCS. This equation is actually, we have seen how to calculate the drainage coefficient and all. Cypress Creek formula, many formulas were there. We have discussed everything. But this is a new formula which is used exclusively for finding the drainage coefficient in case of subsurface drainage system design. So this formula is given by United States Soil Conservation Services, which is derived in 1973. By as per them, the drainage coefficient is equal to P plus C into I by F. All the quantities are given here. So this is the equation used for finding the drainage coefficient in case of subsurface drainage system design. Okay. And after finding the drainage coefficient, we can easily find the capacity of the drains, because the capacity of the drains is found out by Manning's equation. In the surface drainage system also we have seen this. Capacity is calculated by means of Manning's equation. So Manning has derived an equation for this. There is no R here. Actually V is equal to 1 by N R raised to 2 by 3 S raised to 1 by 2. This is the equation for velocity by Manning's. When velocity is there, we can find the capacity by multiplying it with area. Capacity is equal to velocity into area. So we can easily find the capacity of the drainage system. The minimum velocity of flow should be 0.4 millimeter per second. It is generally this much amount of velocity should be allowed in a subsurface drainage system. Okay. And the other things here is N R and S. So the values which is depending on the velocity are N, R and S. R is the hydraulic radius, S is the slope of the particular area. So the minimum longitudinal slope where siltation is not a hazard is 0.1% for 10 centimeter diameter tile and 0.05% for 15 centimeter tile. So S is the slope of the area. So the slope of the area should be 0.1% or below 0.1, above 0.1 percentage in case if you are using 10 centimeter diameter tile, and it should be greater than 0.05 percentage when we are using 15 centimeter diameter tile. So the slope should be a factor. So slope is actually a factor for calculating the capacity of the drain. Okay. And another factor is Manning's coefficient. Its value for clay and concrete pipe should be N is equal to 0.013, and for corrugated plastic pipe N is equal to 0.05 to or 0.15 to 0.02. So we will use many materials for the tiles. We will use plastic pipes, we will use concrete pipes, clay pipes, etc. So we will see the materials of the pipes later. But according to the material, the N value changes. N is actually the roughness coefficient. For clay and concrete, it will be somewhat between 0.013 and closer to 0.013, and for plastic it will be like this. And the minimum longitudinal gradients where siltation is, so this thing we have discussed earlier itself. So this is about the capacity of the drains. Now we will move on to the fourth step, that is the size and grade of the tile drains. Once we have calculated the capacity of the tile drain, now we can easily calculate the size. Size is actually the diameter of the tiles. The collector drains are usually installed with sealed joints. So we will install the collector drains with sealed joints. That is, the main drains we will install with sealed joints. The diameter of the collector drain is successively reduced at the upstream by means of suitable transition section. So in the main lines, the main lines will be joined each other. Main line, we are installing pipes everywhere. So main pipe will be joined each other. Okay, joined by use of some sealings and all. But laterals will not be joined. And the collector drains are designed to carry the required flow without any internal hydrostatic pressure and to prevent water backing up into the open joint lateral drain pipes. So this is a logical thing. Size of the collector drains should be determined from the drainage area of all the connected tile drains. Okay, the main pipe size will be determined from the total drainage area, how much amount of water is there and how much amount of water should be carried by this main. So like that we will calculate the size of the main drains. Collector drains means actually the main drains. And diameter of a drain lateral is usually selected for minimum flow at the lower end, and the minimum diameter should be 10 centimeter. 10 centimeter. Normally we will use 10 centimeter pipes for constructing the laterals, and smaller diameter than this causes clogging in the pipes. If you are using smaller than this diameter, it will cause clogging in the pipes. So that is the thing. And for main drains, larger diameters will be used. It can be up to 75 centimeters. And if we don't have any particular size of what is that pipe material, then we can calculate the diameter of the tiles. If we are not guessing, or we are not assuming the size of the pipe, in some cases we can assume the size of the pipe by calculating the capacity. If you know the capacity, then we can assume a type of pipe. But if you are not assuming any type of pipe, then we can calculate the diameter of the tile drains by means of this equation. This is actually Manning's equation. Manning's equation is equal to V is equal to 1 by N R raised to 2 by 3 S raised to 1 by 2. So this is the equation. 1 by N, this is R. R is equal to A by P. Area of the pipe divided by perimeter of the pipe. The whole raised to 2 by 3 into S raised to 1 by 2. And capacity is equal to A into V. So this is V. This is A. A is the area, pi by 4 d square. So this is actually Manning's equation. Relation for Q according to Manning's equation. From this we can calculate the D value by this equation. So this is the final equation for D. So by using this equation you can easily find the diameter of the tile drains. The second thing in this step is grade of the tiles. So we have found out the diameter of the tiles. Now we have to place the tiles in a particular slope. Okay, if there is slope, then only the water can flow. Okay, then the pipes should be placed in a particular slope. How much slope will we have to give? Okay, actually the slope should be selected in such a way that there will not be any silting in the pipeline. The particles which are carried by the water should not be silted or sedimented in the pipelines. So the velocity or the grade should be in such a way that there is no silting inside the pipeline. The minimum grade should not be less than 0.1 percentage for 10 centimeter tile and 0.07 percentage for 12.5, 15 and 17.5 centimeter tiles. So for these diameter tiles, grade should be 0.07 or greater than that. For 10 centimeter tile, the grade should be 0.1 percentage or greater than that. And the steepest slope should not exceed 2 percentage. Okay. If the grade of a tile mean at any point is greatly reduced, it is necessary to protect the drain from blowouts caused by hydrostatic pressure by providing a pressure relief well. When the grade is too much low, then what will happen at the main line? When the water is reaching at the main line, a large amount of water will be reaching at the same time. So what will happen? There will be higher hydrostatic pressure that may cause the bursting of the pipe or blowing out of the pipe. Okay, in that case, for reducing the hydrostatic pressure, we can place some pressure relief wells or some valves at some places nearby the main lines. Okay, so this is a provision for reducing the pressure inside the pipe due to the lesser grade. And this is about today's lecture.